Hi all, welcome back to Computer Organization course. We'll get started.
In the last class, we had started about the interrupts and we had seen this example. Then we had also discussed that whenever the devices, if they want to, request for the interrupt, what they will do is they will use a bus line, that is interrupt request line, right? So from that request line, it would tell the processor that uh, I am raising a request, something like this. So we should note that as part of handling requests, the processor it must inform the device that its request has been recognized so that it may remove the interrupt request signal. So whenever a device it interrupts or it raises a interrupt signal, your processor has to acknowledge that particular device. So how this can be done is like your processor it there is a signal called as interrupt acknowledge signal. So your processor would it would activate this particular signal, that is interrupt acknowledge signal, so that the devices they'll come to understand that okay, my request, whatever the interrupt I have raised has been or will be satisfied by the processor. Okay, so after that there is an alternative approach to this one, that is the transfer of the data between the processor and the I/O device interface accomplish the same purpose. Instead of your interrupt acknowledge signal, we have the data transfer between your processor and the I/O device interface. The execution of an instruction in that interrupt service routine that accesses a status or data register in the device interface, it informs the device that its interrupt request has been recognized. Okay, so far we have seen that interrupt service routine is very similar to the subroutine like this one. So whenever interrupt occurs, it would execute a routine. So we have seen this one. So again, a subroutine it performs the function required by the program from which it is called. Again, however, we have to note that the interrupt service routine may not have anything in common with the program being executed at the time the interrupt request is received. In fact, the two programs they belong to often they belong to different users. So therefore, before starting the execution of your interrupt service routine, any information that may be altered during the execution of the routine, it must be saved. So this information must be stored again restored before execution of the interrupt program is resumed. In this way, the original program can continue execution without being affected by any of the interruption, or they can expect some delay, but uh, it won't hamper any execution process. Okay, next we will see the interrupt hardware, right? So this is a diagram, it shows the interrupt hardware. So here we have multiple devices, that is this is device 1 2 up to n devices. So these devices have the switches. Okay, so we'll talk about that later. So this is a bus and this is called as interrupt request line. Okay, so in this interrupt hardware we already pointed out in the earlier sessions that IO device request an interrupt by activating a bus line, and that bus line we call it as interrupt request, which is this line INTR, interrupt request. Okay, then a single interrupt request line may be used to serve n devices. So as seen in the picture, so there is a single interrupt request line where you have multiple devices connected to it. So all these devices they are connected via switches to ground. So there is one device here, device 1, it has this switch and this switch is connected to ground. Likewise, we have n number of switches, those are connected to particular devices. So whenever a device it want to request an interrupt, so what it has to do is it has to close its switch. Suppose this device 1, okay, that is one device, it has a switch. Okay, now this device 1 it has to raise the interrupt. Okay, what it has to do is like it has to close this switch. Right now it is open, it has to close this switch, something like this. Whenever the switch is closed, it would be a straight line, right? Okay, this is a straight line over here, right? Whenever the device want to request a interrupt, So it has to close this switch.
So if all the interrupt request signals, that is from INTR1 to INTRN, all these are inactive, that means if all these switches are open, then the voltage on this line, interrupt request line, will be equal to VDD. Okay, whenever all these are open switches, the voltage across this line will be equal to VDD. So this is the inactive state of this line. So when a device it requests an interrupt by closing its switch, something like this, then the voltage across this line it drops to 0. It causes the interrupt request signal INTR received by the processor to go to 1. Why? Because we have negation over here. Okay. Since the closing of one or more switches will cause the line voltage to drop to 0, the value of INTR is the logical OR of the request from the individual devices. That is, this INTR, it is equal to INTR1 plus INTR2 plus till INTRN. It is the logical OR operation. We should note here that the use of INTR bar, this complement, right? Why this is used? Because to name the interrupt request signal on the common line, because the signal is active when the voltage is low. Getting it? Now let's move on to enabling and disabling of the interrupts. Okay. So during execution, the programmer should be given a complete control over the events. Like when a set of instruction has to be executed, then what set of instructions would be executed, something like this. The control has to be given to the programmer. The arrival of any interrupt request from the external device, it will cause the processor to suspend what it is doing, that is the execution what it is doing, and start or serve the another program or the interrupt which has received. Because the interrupt can arrive at any time, you may not know, right, at this particular time the interrupt would occur. It is unpredictable. So the interrupt can arrive at any time, so that they may alter the sequence of the events from the predicted by the user or the programmer. Hence, the interruption of the program execution must be carefully controlled. So there are situations in which the processor should ignore the interrupt request. So what are those situations? We have two situations like this. The first one is an interrupt request from the printer should be accepted only if there are output lines to be printed. After printing the last line of a set of n lines, interrupt should be disabled until another set becomes available for printing. If suppose your output device is printer and it has raised a interrupt saying it is available for printing now, so this interrupt request should be accepted only if your printer has something to print. It has some characters or lines to be printed. If not, it should not be entertained. Say suppose the processor is now executing, or the printer is now printing the output lines. Say after printing the last line in the set of n lines, say suppose your printer is having 10 lines to be printed. Say suppose the 10th line is getting printed. Okay, so your processor has to check now whether the printer has another 10 set or 10 lines of characters or codes it has. If the printer does not have another 10 set or 10 lines of sentences or 10 lines to be printed, the interrupt should be disabled. So your printer has to be given a chance only when it has a number of lines to be printed. If it does not have those many lines to be printed, then the interrupt from the printer should be disabled. Okay. So the second one is, it may be necessary to guarantee that a particular sequence of instructions is executed to the end without interruption, because the interrupt service routine may change some of the data used by the instructions in question. This means, so whenever there is an interrupt service routine, suppose this is our interrupt service routine and there are many instruction in it. So your processor has to make sure that whenever it is, executing the last or few sets of instruction in a interrupt service routine, there is no interruption in that. That means whenever these sets of instructions are executing, any interrupt should not occur. Even if it occurs, it has to disable it. Why? Because this your interrupt service routine, it may be executing, or it may be changing some of the data in while execution. So whenever there is any instruction or interruption that comes in between while execution of specific or a particular order of instruction in interrupt service routine, that interrupt has to be ignored. Okay. So for these reasons, some means of enabling and disabling interrupts must be available to the programmer. Now we'll see how can a programmer, he'll be able to enable and disable the interrupts. Okay, so we will consider in detail the specific case wherein a single interrupt request from one device. So as we all know, there is one interrupt request line and multiple devices would be connected to it. In this our example, we will just consider a single device sending the interrupt request. Okay, now your device, it activates the interrupt request signal. Now it keeps the signal INTR bar, that signal, activated until it learns that the processor has accepted its request. This means that your interrupt request signal will be active during the execution of your interrupt service routine until an instruction is reached that accesses the device in question. It is essential to ensure that this active request signal, it does not lead to successive interruption. So whenever we have successive interruption, it will go into our system, it will go into infinite loop. Okay, and from that infinite loop it can't recover. So to solve this problem, we have again many solutions. The first solution is that your processor hardware should ignore the interrupt request line until the execution of the first instruction in the interrupt service routine has been completed. That means your processor, say suppose there is a interrupt request from any of the device, and your processor, it has jumped, or it's being starting the interrupt execution of the interrupt service routine. Now before that, your processor hardware should be such that it should ignore the interrupt request line, that is INTR bar, that line, until the execution of the first instruction in the interrupt service routine has been completed by using an interrupt disable instruction as the first instruction in your interrupt service routine. So by this way, the programmer can ensure that there is no further interruption will occur whenever your interruption enable instruction is executed. The second option is here, which is suitable for a simple processor wherein it has only one interrupt request line, is to have a processor automatically disable the interrupt before starting the execution of the interrupt service routine. The last option is that your processor, it has the special interrupt request line for which interrupt handling circuit, it responds only to the leading edge of the signal. So such line is said to have edge triggered. So whenever you have that leading edge of the signal, then the interrupt handling circuit would respond. So in this case, the processor will only receive one request regardless of how many lines are activated, but it would accept only one, or it receive only one request. So there is no danger of multiple interruptions and no need to explicitly disable the interrupt request from this line. So to summarize, the sequence of events involved in handling an interrupt request from a single device. So first we'll assume that the interrupts are enabled. Now we have a typical scenario. These are the typical scenarios. The first one, the device raises an interrupt request. Then the processor interrupts the program which is currently being executed. So the first this point, it says that it says there is a device which has raised an interrupt. Now your processor has to respond to that particular device. So your processor, what will it do? It interrupts whatever it is executing at this point. It will stop that. Now the third one is that interrupts are disabled by changing the control bits in your processor status register. So whenever the interrupts, the processor has got the request, it will disable the control bits in the processor status register, except for the case that for the edge triggered interrupts. So those cannot be, there would be only one request, so no need to disable that. Next,
the device is informed that the request has been recognized, and in response it deactivates the interrupt request signal. So your processor has to inform the device that its interrupt has been recognized by sending a acknowledgement. Then what it does, it deactivates the request raised by that particular device. Next point is the action requested by the interrupt is performed by the interrupt service routine. Now your processor has to serve the interrupt, serve the particular device which has raised the interrupt. How it will serve? By executing the interrupt service routine. The last one is that interrupts are enabled and execution of the interrupted program is resumed. That means your processor has previously disabled the interrupts, or that getting of the interrupts request. So now it will again enable it, then your execution of the interrupted program. In the second point, the processor has stopped some program which is executing, right? So it will continue from that, or it will execute wherever, or it will resume the interrupted program. Okay.
Okay, now let's move on to handling of multiple devices. So we will assume that, or we will consider a situation where you have n number of devices, they are capable of initiating the interrupts that are connected to the processor. So let's first check the diagram, right? This is a simple diagram which we have already seen, wherein we have n devices. They are connected to this interrupt request line, which is again connected to the processor. Now we will consider this situation wherein these multiple devices, right? There are n devices, and these devices are capable of sending the or initiating the interrupt at the same time, or multiple requests are coming from the devices. Then what will happen? So, because these devices are operationally independent, so there is no definite order in which they will generate the interrupt. For example, you have the device 1 here, device 2, likewise device n. It is not necessary that device 1 will initiate the interrupt first, then device 2, so on. It may be a situation that device 3, which is here, it will first initiate the interrupt, then device 1, then device 2. This situation can happen, or in at the same time, these multiple devices can request the interrupt or initiate the interrupt. Now what will happen is it will lead to number of questions, such as how can the processor recognize the device requesting an interrupt? If multiple devices are sending or initiating the interrupt at the same time, then how can the processor recognize the device requesting an interrupt? Second question is, given that the different devices are likely to require different interrupt service routine, how the processor will obtain the starting address of the appropriate routine in each case? That means, say suppose we have, okay, whenever the interrupt occurs, we know that its particular interrupt service routine has to be executed. If suppose multiple devices, they'll raise a interrupt, and these multiple devices or the request what they raise, they might need some different interrupt service routine to be executed. Now it is a confusion to your processor, like which service routine to execute. Not which service routine, but basically the starting address of this service routines. Okay. Then the third one is, should a device be allowed to interrupt the processor while another interrupt is being serviced? That means, say suppose this device 1, it has raised an interrupt, and its interrupt service routine is being executed. At the same time, another device, this device 2, it will raise an interrupt. Then what will happen in this case? Should the processor be allowed to interrupt this execution and move on to this one? The fourth one is, how should two or more simultaneous interrupt requests be handled? Okay, if two devices will send the same, will initiate the interrupt at the same time, then what will happen? Which device to give the priority? These all conditions or the questions will come into mind when we say that handling, or the devices, they say they initiate the interrupt request. So the means by which these problems are resolved vary from one computer to another, and the approach taken is important considering or consideration in determining the computer's suitability for given application. When a request is received over a common interrupt request line, as shown in this figure, we have a common interrupt request line, right? So if a request is received over this one, so additional information is needed to identify the particular device that has activated this line. If two devices have activated the line at the same time, it must be possible to break the tie and select one of the two requests for the service. So, when the interrupt service routine for the selected device has been completed, then the second request can be serviced. The information needed to determine whether the device is requesting an interrupt is available in the status register. This is the processor status register. Okay. So, when the device raises an interrupt request, it sets to 1. It sets to 1 of its bits in the status register. Let me show you the other diagram. This one, right? So we have status register. So here, this is for keyboard. Okay, IRQ is interrupt request. So this is keyboard interrupt request, and this is display interrupt request. Okay, we'll consider one of these examples then. So say suppose when a device, say suppose your keyboard, okay, so keyboard has raised a interrupt request, then what it has to do is it has to set this bit in the status register to 1. Okay, now this bit is interrupt request bit. For example, these two, this is for keyboard and this is for display. This is the simplest way to identify interrupting devices is to have the interrupt service routine poll all the IO devices connected to the bus. The first device encountered with its IRQ bit set is the device that should be served. An appropriate subroutine is then called to provide the requested service. This means when two devices, they'll send the interrupt, when they initiate this interrupt request at the same time, what happens is like its status registers like this one. Say suppose we'll consider this keyboard and mouse here. This keyboard and display are the devices, and they have sent the, or they have activated this interrupt request line at the same time. Now it is the processor, it has to decide which one to serve first, right? So what your processor does is there is a program called as interrupt service routine. So this routine, there is a program which is running all the time in the processor. What this program will do is it will continuously track these IRQ bits of the devices. Okay, so why? Because now this continuously tracking of the IRQ bits of the devices, we call them as call this process as polling. Okay, so the first device encountered with this IRQ bit set as 1 would be served first, then the next one. Okay, if your interrupt service routine, it finds out that suppose the keyboard has this status as set 1, the status bit as set 1, then it would be, this keyboard's interrupt service routine would be executed first, then the next device which has set its status bit as 1, it would be served. Now this polling scheme, it is easy to implement, but the only disadvantage here is the time spent interrogating the IRQ bits of the all the devices that may not be requesting any service. If suppose we have n devices, say suppose only these two devices have activated this line, but your polling scheme, what it does, your interrupt service routine, what it does is like it checks all these devices, all the devices status bit. It will continuously check. So the time spent would be greater in this situation. Next, we'll study about the vectored interrupt. So in the last slide, we had seen about handling of the multiple requests, right? And we had seen a polling scheme, right? Wherein the interrupt service routine would continuously check the status bits of the devices, which has by then it will understand that which device to serve and all. So the main disadvantage over there was the time spent. So to reduce the time involved in the polling process, so the device, the input or the output, the devices whichever is they are connected to the processor, what they can do is like they can identify themselves, okay, to the processor. So, a device requesting an interrupt may identify itself directly to the processor. Now, this we call it as a vectored interrupt. This means, instead of your interrupt service routine continuously checking or continuously polling the devices, the device which raises the interrupt, it will directly or it will identify itself to the processor. So it is easier for the processor now to immediately start executing the corresponding interrupt service routine. Now, the term vectored interrupt, it refers to the all the interrupt handling schemes based on this approach. The basic concept what you have to understand here is the devices requesting an interrupt, it identifies itself to the processor. That is a vectored interrupt. Now, whenever a device requesting an interrupt can identify itself, how to identify, right? How to tell the processor that I have raised a interrupt. So what it can do is like it will the devices that need that sends or that initiate the interrupt itself, or it identifies itself by sending a special code over the bus. Special code, the devices will send a special code to the processor saying that I have some interrupt, please you serve it. So this is the special code the device would send to the processor over the bus, that is by using the data lines of the bus. Okay, so then what will happen is, so whenever the processor receives the special code, so it enables your processor to identify the individual devices even if they share a single interrupt request line. So in the last slides and all, we had seen a diagram where we had a processor and n devices were connected to it, and all these devices would share a common or a single interrupt request line. So whenever the device sends a special code to the processor, even if multiple devices are connected to that line, so it is easier for the processor to recognize the device. The code supplied by the device, it may represent the starting address of the interrupt service routine for that device. It means, say there are five devices connected to the line, to that interrupt request line. So these five devices may have five different interrupt service routines. Whenever they raise interrupt, those particular or corresponding interrupt service routine have to be identified or executed. So this special code we had seen, right? The devices would send a special code to the processor in vectored interrupts. So this special code, what it can represent is like it can represent the starting address of the interrupt service routine for that particular device. Again, the code length, it would typically range from 4 to 8 bits. The rest of the reminder address, it is supplied or it is done by the processor based on the area in the memory where your interrupt service routines are located. So in many computers, this can be automatically done. Okay, or automatic interrupt handling mechanism is used for this purpose. The location pointed by the interrupting device is used as the starting address of the interrupt service routine. Then your processor reads this address, that is the special code. It will call, that particular thing we call it as interrupt vector, and it is denoted by L. And this address will be then loaded into your program counter. So the interrupt vector may also include a new value for the processor status register. In most computers, IO devices send the interrupt vector code over the data bus using your bus control signals to ensure that the devices do not interfere with each other. When a device sends an interrupt request, the processor may not be ready to receive this vector code immediately. For example, it must first complete the execution of the current instruction which is which the processor is executing. So for this instruction to be execution to be completed, that might require the use of bus. So there may be further delays if the interrupts happen to be disabled at the time the request is raised. The interrupting device must wait to put the data on the bus only when the processor is ready to receive it. When the processor is ready to receive the interrupt vector code, it activates the interrupt acknowledge line, that is INTA line, interrupt acknowledge from processor to the devices. The IO device responds by sending your interrupt vector code and turn off the interrupt signal. So this is a vectored interrupt description. So what you have to understand in the vectored interrupts is like, instead of your processor checking or polling the status bits of the devices. The device that require a service, it will interrupt or it will send its special code, that is the vector, interrupt vector, that is L, that is your special code to the processor. That is the device will identify itself to the processor. Okay, so this you have to remember. Next, you have a quiz. The device requesting an interrupt identifies itself directly to the processor is known as dash. You have got a minute of time to respond. Okay, time up. That's it for today. We'll conclude our session. Thank you.